Welcome to the deep dive. Today we're diving headfirst into something really critical if you're involved in or even just curious about blockchain and decentralized applications, especially on the Cardano platform.
Yeah, it's a big topic.
Definitely. We've been sifting through quite a bit of information, looking at, everything from the real nitty-gritty details of code flaws to the pretty advanced techniques used to stop them.
That's right. And our goal here really is to pull out the most important concepts and examples of potential pitfalls in smart contract design on Cardano.
Mm-hmm.
We want to give you a clearer picture of the kinds of things developers and security experts are, let's say, wrestling with every day to build and secure applications in this ecosystem.
Sort of like a crash course in the specific security landscape for Cardano smart contracts.
Exactly that. Think of it that way.
Okay. And we're not going to get totally lost in the super deep technical weeds, but we do want to highlight the specific types of vulnerabilities that pop up and, why they matter.
Right. So let's get into it.
So let's unpack this. To start, I think we really have to talk about what makes Cardano a bit different under the hood.
Absolutely. You have to understand the foundation first. It's key. So unlike platforms like, say, Ethereum, which use an account-based model, you can kind of think of that like a bank account where you just have a single balance.
Right, just one number.
Yeah. Cardano operates on something called an extended UTXO or UUTXO model. It's an evolution of the model Bitcoin uses, but importantly, it has the ability to attach complex data and logic.
Okay, so instead of just balances in accounts, you're dealing with these distinct, unspent transaction outputs, so the UTXOs.
Mm-hmm.
They're like individual digital coins or notes almost. Each with a specific value and maybe some associated data.
Precisely. And the extended part is crucial. It means they can hold arbitrary data, which is absolutely essential for representing smart contract state. And here's where it gets really interesting and directly shapes the vulnerability landscape we're talking about. A fundamental property of UTXO is that each individual UTXO can only be consumed, meaning used as an input to a transaction by one single transaction within any given block.
Only one.
Only one per block. It's like, imagine each physical note in your wallet can only be spent once in a single shopping trip, even if you have multiple notes.
Okay, that sounds like it could have some serious implications for smart contracts. I mean, if multiple people want to interact with a contract state, and that state is often held in a single UTXO, does that create a kind of bottleneck?
It absolutely does. And this leads directly to what's known as the concurrency issue, or sometimes contention.
Right.
If a smart contract's main state or a key piece of it is held in a single UTXO, then only one transaction in a block can successfully update that specific UTXO by spending it and creating a new one.
So what happens if, 5 people try to do something with that same UTXO in the same block?
Only one will succeed. The others will fail because the UTXO they were trying to spend, it's already gone. It's been consumed by the first successful transaction.
Wow, okay. So developers building on Cardano, and they're using Plutus, which is based on Haskell. They have to design their applications specifically to handle this, right?
Exactly. Plutus scripts are essentially these validator functions attached to the UTXOs, and they define the rules for how that UTXO can be spent. But this whole EUTXO structure means the validation logic applies to the inputs being spent, rather than modifying some kind of global contract state directly.
That input-centric validation. Okay.
Yeah, understanding that and the concurrency constraint is absolutely fundamental. It means, on the one hand, certain classic vulnerabilities you see in other platforms are basically non-issues here. But on the other hand, it introduces a whole new set of potential pitfalls, specifically around how you manage and validate these UTXOs and their associated data and tokens.
Okay, all right. So with that ETXO and Plutus context in mind, what are some of the concrete ways developers might trip up? What specific kinds of vulnerabilities actually show up in Plutus scripts?
Well, the information we've looked through highlights several common patterns. One is something called the other redeemer vulnerability.
Other redeemer.
Right. So when you spend a UTXO locked by a script, you provide data, right? Both a datum, which is like the state, and a redeemer. The redeemer often signals what action you intend to take, think like deposit or withdraw.
Okay, like telling the script which function or path to execute.
Pretty much, yeah. Now, imagine a script where the logic for one action, let's say withdraw, implicitly relies on a maybe checking a deadline or something that's only performed if you use the deposit redeemer.
Uh-oh.
Yeah, a malicious user could potentially craft a transaction to withdraw funds, but they provide the deposit redeemer instead of the withdraw one. If the script isn't written carefully enough to ensure the correct redeemer is used for the intended action, or if logic isn't properly separated.
They could bypass the check needed for the withdrawal by basically pretending to deposit.
Exactly. They essentially lie about their intent via the redeemer. The impact is pretty clear. Bypassing security checks you thought were protecting the withdrawal path.
Oh, okay. So you have to be incredibly precise about how redeemers control the logic flow.
Absolutely. You need to ensure all necessary checks run regardless of which valid redeemer is used, or strictly enforce that only specific redeemers can trigger certain logic paths. It demands really careful thought about all possible execution paths.
Makes sense. What about handling tokens? Cardano has native assets, which work a bit differently than, say, ERC20s. Does that create unique issues?
It certainly can. That leads us to another one, the other token name vulnerability. This is a really interesting one, quite specific to Cardano's token model.
Oh, so?
Okay, so on Cardano, a token is identified by two things. Its currency symbol, which is derived from the hash of the minting policy script.
The script that controls creating the token.
Right, and its token name, which is just a string, up to 32 bytes long.
So maybe like a main identifier, the symbol, and then a specific sub-identifier, the name, like policy-ID and my token 1.
Precisely. Now, a common mistake in a minting policy script, the script controlling creation, might be to check only that a transaction is minting a very specific asset class. That means checking for a specific currency symbol and a specific token name. Let's call it legit token.
Okay, seems reasonable. Check for the right token.
But they might forget to add a check that explicitly prevents the minting of any other token name under that same currency symbol in the same transaction.
Ah, I think I see where this is going. So the policy might say, yes, minting legit a token with symbol X is okay, but it doesn't say, and you cannot mint fake token with the same symbol X at the same time.
You've got it. And if other parts of the protocol, maybe another script or some off-chain dApp logic, only checks the currency symbol to identify the project's tokens.
Then that fake token could potentially be passed off as the real deal, or used where only legit tokens should be.
Exactly. It could cause all sorts of problems. The impact could be leaking valuable protocol tokens or enabling unauthorized actions by essentially impersonating a legitimate asset. It really highlights the need to lock down those minting policies to only allow the intended asset classes under that symbol and forbid all others.
That's a fascinating example of how the platform's specific design choices create these unique vulnerability types. Good. What about the data stored in the UTXOs? You mentioned they carry a datum for state.
Right. That brings us to the arbitrary datum vulnerability. Smart contract UTXOs, as we said, use datums to store state information. Now, a developer might think, okay, when this UTXO gets spent later on, my validator script isn't going to actually read or use the specific data inside the datum for its validation logic.
So they think, I don't need this data for the next step, so I don't need to worry too much about what's in it when I create it.
Sort of, yeah. They might not put rigorous checks on the datum's structure or content when the UTXO is created because their spending logic doesn't directly reference it.
And why is that dangerous? If you're not using the data, what's the harm if it's, well, arbitrary?
Here's the subtle trap. Even if the validator script doesn't use the datum's value, the underlying EUTXO system, the Cardano ledger itself, still requires that the type of the datum attached to the UTXO matches the expected type defined in the validator script's logic.
Wait, the type has to match, even if the content isn't checked by the script.
Exactly. So if you lock a UTXO with a datum that has the wrong type, let's say your script expects the datum to be an integer representing a count, but you accidentally lock it with a datum that's just a text string, any future transaction attempting to spend that UTXO will simply fail validation.
And it fails at the ledger level, like before the Pluto script even gets a look.
Precisely. It fails before your script's logic even runs, regardless of whether your script would have otherwise passed based on other conditions.
Wow. So it's not about what's in the data, but the actual structure, the type of the container holding the data has to be right.
You got it. If you create a UTXO with a datum of the wrong type, it effectively becomes unspendable. The impact here is potentially locking funds in those UTXOs forever. If these are critical UTXOs holding protocol state, it could even halt the whole protocol.
That's a really subtle but critical point about the strictness of the EUTXO model. It sounds like you have to be incredibly precise about data types right from the beginning.
You absolutely do.
Okay, what about like The size of the data, or the sheer amount of different tokens in a UTXO, or even the number of inputs being spent, can that cause issues?
Yes, and that's related. These are often grouped as unbounded datum, unbounded value, and unbounded inputs vulnerabilities. They happen if a validator script doesn't put proper limits on things.
Limits on what, exactly?
Limits on the size of the datum it accepts when creating an output UTXO,
Hmm.
or on the total number and variety of different tokens held within an output UTXO, or on the number of inputs locked by the same script that a single transaction is allowed to consume.
And what's the risk there? Does it just become, I don't know, inefficient or messy?
It can be much worse than messy. It can lead straight to resource exhaustion.
Resource exhaustion, like using too much processing power.
Exactly. Plutus scripts and the transactions executing them have strict limits on the amount of CPU and memory they can use within a block. These are the execution unit limits. If a validator allows, say, an arbitrarily massive datum, or an output stuffed with thousands of different token types, or tries to process an unlimited number of inputs from its own script address in one go.
The transaction trying to spend that UTXO might just hit those limits and fail.
Precisely. The transaction fails validation because it ran out of execution budget. And again, you can end up with unspendable outputs, or you could even stall critical parts of the protocol if transactions consistently fail due to resource limits being hit because of unbounded elements.
So you need defensive checks, not just on the core logic, but also on the sheer scale of the data, or the assets, or the number of things being processed.
Yes, you absolutely have to build in reasonable limits that ensure any transaction interacting with your script stays well within the network's operational parameters. It's about preventing denial of service through resource exhaustion.
Okay, this EUTXO model applying logic to inputs.
Yeah.
It keeps coming up. What happens if a single transaction needs to spend multiple UTXOs that are all locked by the same script? Is that common?
It can be, especially in pooling or batching scenarios. And this brings up a really critical vulnerability pattern called multiple satisfaction.
Multiple satisfaction. Sounds bad.
It is, because the validator script runs independently for each script input being spent in a transaction. A naively written script might not correctly handle the situation where a transaction is consuming, say, 2 or more UTXOs locked by that same script.
Can you walk me through how that could be exploited?
Sure. Let's imagine a simple pooling script. To take one token X out of the pool, the rule is you have to put one token Y in. A validator script for spending a UTXO from this pool might check something like, is at least one token Y present somewhere in the transaction's inputs or outputs?
Seems like a basic check.
Right, but watch this. What if a user crafts a transaction that includes 2 separate UTXOs from this pool as inputs? So they're trying to take 2 tokens X out, but they only provide 1 token Y in total in the transaction.
Okay.
Now, when the validator runs for the first input UTXO, it looks at the whole transaction and says, yep, I see a token Y present, check passed. Then when it runs for the second input UTXO, it looks at the same transaction again and says, yep, still see that token Y, check passed.
Whoa. So the single token Y satisfies the condition for both withdrawals.
Exactly. The vulnerable script allows the user to spend both pool UTXOs, getting 2 tokens X, while only putting in the required input, 1 token Y, once. They've essentially doubled their output for the required input.
That's a huge loss for the pool or the protocol.
Yeah.
Definitely a major vulnerability.
Absolutely. The impact is leaking protocol tokens, allowing unauthorized withdrawals, or enabling other unintended actions. To prevent this, developers need to write validator logic that correctly aggregates conditions across all inputs from that script address within the transaction.
So it needs to check, like, okay, there are 2 script inputs here, so I need to see 2 tokens Y being provided.
Precisely. It needs to ensure the total inputs satisfy the total required conditions for all the script's outputs being produced or actions being taken in that single transaction. The sources we looked at also mention a common but insufficient fix, just checking that only 1 input from the script address is present in the transaction.
Why is that insufficient?
Because clever attackers can sometimes bypass that by splitting their funds across multiple UTXOs that are locked by the same script credential, the same logic, but maybe have different staking credentials attached. So the check for a single address might pass, but they still manage to exploit the aggregation logic flaw.
Wow. That really drives home just how complex the state management and aggregation logic needs to be when dealing with multiple UTXOs in one transaction on Cardano. It's a total different way of thinking compared to just updating a single global variable in an account model.
It fundamentally changes how you approach writing and securing the contract logic, yeah. Finally, one more Plutus-specific pitfall that was mentioned is something called insufficient staking key control. This can crop up when a script needs to send ADA to a user's address, specifically a public key hash address.
Okay, just sending funds back to a user seems simple enough.
You'd think. But an address on Cardano has two parts. The payment credential, usually a public key hash, which determines who can spend the funds, and the staking credential, which determines where associated staking rewards go.
Right, the two keys.
Now, if the script only validates that the ADA is going to the correct public key hash, the part that lets the user actually spend the funds later, but it completely fails to check or enforce anything about the staking credential part of the destination address.
Then someone could construct an address that uses the correct public key hash, so the recipient gets the ADA, but attaches an arbitrary or maybe even a malicious staking key to it.
Precisely that. The funds still end up in an address the intended recipient controls because they have the private key for the payment part. But any staking rewards generated by that ADA might temporarily, or even longer, go to whoever controls that arbitrary staking key that was slipped in.
Huh. So the impact isn't losing the main funds, but losing the staking rewards.
Yeah, it leads to unpredictable destinations for staking rewards. It could cause confusion, temporary loss of yield for the user, or potentially benefit an attacker if they can get users to withdraw to addresses with the attacker's staking key embedded. It means scripts need to be really careful about validating the entire address structure they send funds to, not just the spending part.
Okay, so those are some really insightful and sometimes subtle examples of issues that arise specifically because of Cardano's EUTXO model and how Plutus works. But, smart contracts everywhere, regardless of the platform, can face vulnerabilities that aren't unique to Cardano, right? Yeah.
Oh, absolutely. The sources definitely highlight broader smart contract risks that apply just as much to Cardano as anywhere else. A really big one is vulnerabilities that come from interacting with third-party services.
You mean like oracles providing off-chain data? Or maybe calling functions in other smart contracts?
Exactly. If your contract relies on data from an oracle, say, a price feed, you absolutely need to rigorously check that data before using it. Common issues include insufficient checking of return values. Maybe the oracle returned an error code that your contract didn't handle properly, or maybe it provided data in an unexpected format or outside a reasonable range.
And if you just blindly trust it?
Big trouble. Also, using unverified user input when calling these external services can be dangerous, or just relying on services that have undocumented limitations or potential failure modes. Basically, your contract is often only as reliable as the external services it trusts, and you need to validate everything coming from outside.
That sounds like a classic security principle. Never trust external input, right?
That's the one. Then there are mathematical errors. These are a persistent source of bugs in smart contracts totally independent of Plutus or EUTXO.
Like issues with precision when dealing with numbers, rounding errors.
Exactly. The example often cited is about the order of operations like dividing before multiplying with integers, which can lead to drastically different results due to truncation. If your contract is handling significant value, even tiny errors in calculations for fees, interest rates, token swap ratios, or reward distributions can add up really fast and potentially be exploited.
Or maybe just inconsistent calculations.
Yes, using slightly different formulas or rounding methods for what should be the same calculation in different parts of the code. That can lead to internal inconsistencies and state drift, which might open up attack vectors over time.
Those sound like really subtle bugs that could be incredibly hard to spot just by reading the code.
Right.
What about errors in the overall logic or the fundamental design of the contract?
Logic errors are definitely a major concern too. One example mentioned is excessive approval requirements. Imagine a contract where a critical action, like allowing users to withdraw their deposited funds, is locked solely behind the original owner's signature or explicit approval.
Okay, maybe for security.
Maybe, but what if there's no fallback mechanism, no time lock, no multi-sigs, no emergency withdrawal path? If that single owner becomes unavailable, maybe they lose their keys, or worse, become malicious, those user funds could become permanently trapped in the contract.
That would be a complete nightmare scenario for users relying on that protocol.
Absolutely. And even features that are generally seen as useful, like making contracts upgradable, inherently introduce risk, while allowing contracts to be patched or improved over time is often vital for long-term projects.
The upgrade itself could be the point of failure.
Right. If an upgraded version of the code contains a hidden vulnerability, or in the worst case scenario, actively malicious code, deploying that upgrade could compromise the entire protocol and all the funds it holds.
So it's this constant, difficult trade-off between flexibility and security guarantees. It is fascinating, though, that the sources we looked at specifically mention some well-known vulnerabilities that aren't typically considered a major concern on Cardano, precisely because of its EUTXO design.
Yes, and this is a really key point to understand about Cardano's security posture. Re-entrancy attacks, for example, the kind that were famously exploited in the 2016 Ethereum DAO hack, costing millions, are considered effectively impossible on Cardano.
Really? Why is that? What stops them?
It goes back to that EUTXO model and how script execution works. Cardano's smart contracts, the Plutus validators, operate on validating transaction inputs and outputs. Their execution is atomic for a given transaction, and they don't make external calls during their validation process in a way that could allow a malicious contract to re-enter the original contract's logic before its state update is finalized.
So, because the validation is about the whole transaction at once, and the state transition, consuming old UTXOs, creating new ones, happens atomically if validation passes, there's no window for that kind of re-entrant loop.
That's the core idea, yes. The state is effectively updated all in one go as part of the transaction succeeding, preventing that specific recursive call pattern that defines reentrancy. The design is also often said to minimize risks associated with front-running, where attackers try to exploit visibility into pending transactions to get ahead of legitimate users.
Okay, so that's a significant built-in advantage. While there are clearly plenty of platform-specific vulnerabilities like we discussed, and general smart contract risks developers need to worry about, the EUTXO model itself does seem to offer some inherent protection against certain classic high-profile attack vectors.
It definitely shifts the landscape of security concerns. It doesn't eliminate risk, but it changes the nature of the most critical risks developers need to focus on.
Right, so given all these potential pitfalls, the unique Cardano ones, the general ones, how do teams building on Cardano actually try to ensure their contracts are secure before they deploy them, potentially handling millions of dollars in user funds?
Well, smart contract auditing is absolutely critical, isn't it? Getting experienced third-party security experts to meticulously examine the code before deployment.
Yeah, that seems like a minimum requirement these days.
It really is. And audits typically use a combination of methods. There's careful manual code review, where security researchers read the Plutus code line by line, looking for those subtle logic flaws, race conditions, or economic exploits.
Just eyeballs on the code.
Right. Then there are automated static analysis tools, think linters and scanners, specifically designed for Plutus or general functional programming patterns, which can automatically flag known types of vulnerabilities or bad practices.
Like a spell checker for security bugs.
Sort of, yeah. And then there's dynamic testing. This includes writing comprehensive unit tests to check individual functions, property-based testing to check if code holds true for a wide range of inputs, and fuzzing, where you hammer the contract with random or semi-random inputs trying to provoke unexpected behavior or crashes.
So testing it under stress.
Exactly. But no single method is perfect. That's why a combination is key. And for the most critical contracts, especially those handling large amounts of value or core protocol functions, there's another level: formal verification.
Formal verification. That sounds intense.
Yeah.
What exactly does it involve? Is it different from just testing really hard?
It's fundamentally different, yeah. Instead of just testing a bunch of scenarios and hoping you covered the important ones, formal verification uses mathematical logic and proof to guarantee that certain desirable properties of the contract hold true under all possible execution paths and inputs.
You're mathematically proving it's correct, according to some specification, not just observing that it seems correct for the tests you ran.
That's the core idea. You define critical properties like value can never be created out of thin air, or only authorized users can withdraw funds, and then use mathematical techniques and specialized tools to prove that the code logically satisfies those properties. It's incredibly rigorous.
Wow. That sounds like it requires a lot of effort and specialized skills.
It absolutely does. It's very resource intensive, both in terms of time and the expertise needed, but it offers the highest possible level of assurance for the properties you verify. And interestingly, the Cardano ecosystem seems quite keen on formal methods. Perhaps it's influenced by Plutus being based on Haskell, a language popular in academic and formal method circles.
Are there tools being developed specifically for Cardano?
Yes, the sources mention tools like the Smart Code Verifier, which aims to help bridge the gap by translating annotated Plutus code, where developers add formal specifications into proof obligations that automated theorem provers or proof assistants can then try to solve.
So, trying to make formal verification more accessible to developers. What kind of specific properties can you actually prove about a smart contract using these methods?
The sources gave some good examples. Things like validity, proving that any valid state transition defined by the contract logic always results in another valid state, preventing the contract from getting into some broken or undefined state. Liquidity, proving that it's always possible for users who are entitled to withdraw their value from the contract to actually do so, preventing funds from being permanently locked.
That directly addresses the locked funds risk we talked about.
Exactly. Also, fidelity, which is about ensuring the total value managed by the contract is conserved across transactions. No value gets unexpectedly created or destroyed, preventing inflation bugs or unfair value extraction. And it's particularly powerful for proving the absence of issues like that multiple satisfaction exploit we discussed earlier.
Proving that someone can't get multiple outputs by satisfying a condition only once.
Right. Formal methods can mathematically demonstrate that such scenarios are impossible given the contract's logic.
It really sounds like formal verification, while difficult, directly targets some of the most severe potential consequences of smart contract bugs, locked funds, stolen value.
It does, and it provides a much higher level of assurance for those specific properties than testing alone ever could. So really, understanding this whole spectrum from the Plutus specifics shaped by EUTXO, like redeemers and datum handling, to the broader logic and math errors, and then knowing about the rigorous methods like multifaceted auditing and formal verification used to combat them, it's all pretty crucial.
Yeah, whether you're a developer actually building on Cardano or maybe just a user trying to evaluate the security and trustworthiness of the dApps you're thinking about interacting with, it's clear this isn't a trivial undertaking.
Definitely not. It highlights just how much diligence, expertise, and frankly, investment in security is required to build reasonably secure applications in this decentralized space.
Okay, so we've taken quite a deep dive today into the complex world of Cardano smart contract vulnerabilities. We explored the unique impact of the EUTXO model, looked at specific pitfalls in Plutus scripts like redeemer issues and datum handling, touched on more general smart contract risks, and importantly, discussed the critical role of auditing and these advanced formal verification techniques in trying to secure these systems.
Yeah, I think it's pretty evident that while Cardano's architecture does offer certain inherent protections against some attack vectors, developers still face a unique and challenging set of security considerations specific to the platform, alongside the general challenges of building secure software.
It really underscores the need for a multi-layered approach, doesn't it? Combining careful coding practices, really thorough testing, getting professional security audits, and then, for the most critical parts, leveraging these advanced formal methods.
Absolutely. It seems like that layered defense is really non-negotiable in this space.
Which, I suppose, leaves us with a final, maybe slightly provocative thought for you, the listener, to consider. As smart contracts continue to grow in complexity and become more deeply integrated into our financial and digital lives, and as attackers constantly devise new and clever ways to exploit them, can we ever truly achieve absolute 100% unbreachable security for code running on a blockchain? Or is the pursuit of smart contract security destined to be an ongoing, unending battle of vigilance, adaptation, and constantly reinforcing those layered defenses?